target next stage. Because in training, you just keep your softmax function as it is, input the cost function, and then optimize, and then at the end of that network, you put out the soft target, you put on right the next one.
That was my understanding, but if you go to figure 5, it seems like they are using it during training.
No, temperature is used during training, for sure. So you use temperature to train that model, and then you use temperature to train the distilled model, and then you cancel the temperature on test time. So at the final test.
Maybe they do normalization during training, no? That would cancel out the scaling effect.
No, not in the last layer, you don't normalize. So this term here is the normalization of the last layer.
But it seems a bit strange. It looks weird. You might have to train longer in order to get the same accuracy, but because it's really just a rescaling.
I mean, for sure the predictions are broader if you train with temperature. For sure. It doesn't change so that your arg max does not change, but for sure the predictions become flatter.
But the ZIs are not bounded, right? So in principle, because in the previous paper they were arguing, oh, the ZIs can in principle become very, very large. And that was the effect of the distillation, preventing that the ZIs become too large by adding the additional targets to be finite sized. So that's why I'm not sure.
So remember that you're dividing before the softmax. So if these logits look like that, what you're doing is you're flattening this. So your softmax distribution is then.
You know, if your Z are free, they can cancel out the scaling effect of temperature. I think that's what you're trying to say.
Yeah, but the temperature is applied before softmax. So this is not a linear transformation.
But still, that doesn't matter. As long as the ratios are the same, it shouldn't.
Because your cost function comes at the end,
yeah, but there is a change in the cost function because of the temperature. But so it is not going to affect the direction of your gradient for sure. But it is going to affect the shape of your output. And what the trained network is going to output is going to change with respect to temperature.
Once it's trained, yes. Once it's trained and you change the temperature, then I absolutely agree. But during training, I don't feel it.
Oh, we can try it. We've tried temperature. It does give broader predictions. Oh yeah, we can.
Yeah, sure. Sorry.
No worries, it's fine. So what happens is that if that becomes infinity, the predictions either way, even if it's a train or test. If that tends to infinity, those predictions are going to tend to 1 over n for sure, and it's going to give you a flat prediction. So that is what distillation is all based on. And in the previous papers, they were focused on compressing the models. So you would use the targets provided by F to train a new model, which is smaller. But here they want to maintain the structure. So what they do is they train the exact same model, but with the soft targets. So the distillation here is going to be X. This set of X is going to be the same. And this F of X is going to be the same. They call it distilled. But the only difference is that here you're not going to try to predict the actual targets. I ran out of space. But you're trying to predict F of X. Okay? That makes sense? At the beginning it doesn't make much sense because you're not focusing on the main driver for distillation, which is compression. But here you're just saying, well, okay, let's say that this model is learning an actual probability distribution. That means that the softmax output is giving me some structural information about my training data. So the example that they give is that if you imagine an output for a 1, if f of 1 of x, if that is the output, if f of 1 is 0.6, and then f of 7 of x is 0.4, then this model is learning a structure, is learning some of the structure of the data, because actually it would be like that one is very close to that side, right? So it is learning some structure of the data. So your distilled model is not going to learn from the data directly, but it's going to learn from the transformation that was learned before. And at the very limit, if if our optimization algorithm manages to find the global minimum and so on, FD is going to be the same as f of x. In practice, that doesn't happen, and that is why this particular method works against adversarial attacks. Okay. Now, one of the interesting things about this paper, which I think was lacking from the first paper, is that they actually give some intuition on why distillation works. Okay, we're going to go through it a bit quickly because this, I think that the results are are very interesting. But they define three things. So first, the impact of distillation on training. And so the first argument is the impact of distillation on training the network. So the original network that is the cost function. The original network is trained on hard targets, so that function reduces to just ft of x. So where ft is where t of x is the indicator for the actual class, okay? Because that becomes 1, all the others become 0. So you're forcing the parameters to learn very confident classifications. You're telling them just make that activation as high as possible when this input comes in. However, when you train with a soft target, so when you're training the distilled version of x, now it is not trivial to say that all these are 0, right? Because now they are soft. So what you're saying is that now that the weights are trained with the likelihood of the class instead of the hard target of the class. And I just want to say that this is all under the assumption that softmax is giving you a probability distribution, right? That is a discussion for another time. But let's assume that for this paper. So now the outputs are constrained to the likelihood of the class instead of just a hard target. So that is one of the intuitions on why distillation provides better generalization results. The second is how it impacts model sensitivity. If you remember, adversarial attacks are based on how sensitive your model is to small changes in the input. So ideally, we would like to reduce all those big changes. We would like to flatten them so that it's not easy to find a small perturbation that will cause a change in the output. And the reason that works is basically, well, if you take the derivative with respect to any weights, you do a little bit of manipulation. You can see that the derivative of the output with respect to a given input example is inversely proportional to the temperature. So as you increase the temperature, this let's call it prediction landscape is going to be flatter, and it is also inversely proportional to the x. So it's also a 1 over t exponent. So as temperature increases, your perturbations with respect to the input are going to be smaller because of your training. Yeah.
Here it says again for fixed values of the logits, and that is where this might be a wrong explanation for what actually why it works. I think it might be a different reason why it works.
Think of a stable Boltzmann process. Why do you build? You're controlling the temperature, not the molecules.
Huh?
You're controlling the temperature, not the molecules.
Yeah.
And that's a Boltzmann equation, KTO, Kz over T. K is a constant, and Z is something which is an intrinsic part. That's a direction bias.
Well, I can always rescale my temperature and rescale the